Hello everyone, this is Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. And in today's topic, we will see what is the need for generation of mesh and what are the different types of mesh. Basically, we will see what is mesh actually. Okay, so what is mesh and different types of mesh and its use. Okay, so basically what exactly is mesh and where do we use and how it is helpful for real world applications, we'll see, and what are the different types and what are its methodology. So everything we will see in detail. So now basically in the earlier modules already we discussed about mesh, which is the other name is called the grid. So grid or mesh, so basically both are same. So grid or mesh, okay, basically they are same. Okay, now why do we need to generate mesh and or grid? Okay, what is the purpose actually? So when we generate mesh, what happens? So if we don't generate mesh, what happens actually? So and what particular type of the mesh pattern we need to follow for different applications in computational fluid dynamics. So what type of design and what type of element type and what are the number of grid points, so on. Basically these will vary. So let us see a simple representation of a 2D mesh. Okay, so we will go in detail so of each and every element of the mesh generation, and then after next we will see. So we have different arrangement actually. So basically we call it as O mesh or O grid. So next you will have C mesh. Okay, so next you may have H mesh. Okay, so next combination of C and H mesh. Fine. So whatever the combination we have, so it can be categorized in this way. So what is O mesh, what is C mesh, and what is H mesh, and what is CH mesh, and what are the other types, we will see basically. So first let's see the 2D view of a grid or a mesh. Okay, so this is the 2D view. Okay, so here there are 4 surfaces. So phase 1, 2, 3 and 4, the 4 surfaces. So in order to generate mesh, so basically the 4 surfaces or 4 boundaries whatever we have, so we need to assign the points. So let's take this as point 1, 2, 3, 4, 5. So let me take along y direction also. 5, 1, 2, 3, 4, 5. So same. So basically, let's say on the boundary 1 and on the boundary 4, I have taken 5 grid points along. So if we take the coordinate axis, this is x-axis and this is y-axis. Okay. So this boundary 1 is falling under x-axis and is the boundary 4 is falling under y-axis. So when we take the number of grid points along x-axis, so we have 5. And along y-axis we have 5. Okay, so the boundary 1 and 4. So whatever the opposite boundaries, so what is opposite boundary for 1? So we have the opposite boundary for 1 as 3 and the opposite boundary for 4 as 2. So the same number of grid points has to be implemented. Okay, so here 1, 2, 3, 4, 5. So basically the same number of grid points. So it has to be replicated on the opposite boundary. So in order to generate mesh or in order to generate a grid or a grid, so basically first we have to draw the domain. So basically domain is the outer part or the inner part, basically depend on the fluid flow problem. Once we draw or the design the domain, So we have to assign the grid points. Okay. Now when we are assigning grid points, we should actually take proper care. Okay. So if not, it will be very hectic, or it may lead to error. It will not generate mesh. So we'll see in detail after this. Let's see. So what is O grid and O grid or O mesh, C grid or C mesh. So in detail you'll get to know. So what happens if we don't do in this way, or what errors we'll get, we'll be seeing in detail. Now the basic criteria here is, so whatever the number of grid points we use on the boundary 1, so or boundary along x-axis, the same must be replicated or must be implemented in the opposite boundary, which is along x direction. So here we have 5, here we have 5. So therefore with the help of x boundaries, so we will generate y grid lines or y mesh lines. So basically these are called y grid lines or y mesh lines. So these are called y grid lines or y mesh lines. So similarly, the same number of 5 grid points has to be implemented parallel to the y axis. So here we have 1, 2, 3, 4, 5. So same again, all those 5 things we need to implement. Now what happened actually? So first, whatever the points which are located on the boundary are called boundary points. So whatever the points that are located on the boundary or surfaces, so basically those are called the boundary points. So here whatever the grid points, so basically the grid point or the mesh point is obtained by the intersection of x and y grid lines. So here we have x grid lines, here we have y grid lines. So when these two grid lines will meet each other, so the intersection point, this is called a grid point. So this grid point, so basically will be able to locate the position of the fluid particle in finite difference method. We will see in detail, but whatever the grid points which are present apart from the boundary point, so those are called the internal points. Okay, or internal points or internal fields. So there are different names, but in general you can use it as boundary points and internal points, or you can say that internal field points. So anything can be taken. Now, so this is the basic generation of mesh. So how do we generate? First we draw boundaries, then we allocate points along the boundaries. Once we allocate the points along the boundaries, so we draw lines. So basically, let's say we have what we have done. So we have given equal number of points along the x-axis and equal number of points along y-axis for the opposite sides. Now let us consider that we have given unequal points. So what happens, we will see. So when we take the same example again, so let us take this as 1, 2, 3. So here I will take it as 4. 1, 2, 3, 4. So let me take here it as 1, 2, 3, 4. Here let us take it as 1, 2, 3, 4. Let me take it as 5. So here how many points I have taken? I have taken 3 points. Here I have taken 4 points. Here again I have taken 4 points. Here I have taken 5 points. So now what happens when we take the opposite boundaries as different points? So let's see. So when we are drawing lines, so what happens? Let's say this is mapping to this one, and this is mapping to this one, and this is mapping to this one. So this one will try to map any one of this. So let's say it is mapping here. So here you can see that this is forming a negative volume. Okay, so you cannot think that this is generating a wrong mesh. No. So basically we have different types of mesh which we have seen in the previous modules. One is structured mesh, other one is unstructured mesh. So for a structured mesh, so basically the boundaries are regular, and whatever the grid lines we have, x grid lines and y grid lines, so two x grid lines will be always parallel to each other, and two y grid lines will be always parallel to each other. They will never ever meet each other. But here, when we take unequal number of grid points or boundary points along the opposite faces, now what happened actually? So since this grid point does not have any other point to generate the y grid line, so it will go somewhere and form a surface called negative faces or negative volumes. Okay, so this thing, whatever I'm talking, it is in terms of purely for a structured mesh, not unstructured mesh. So for unstructured mesh, this can be accepted. Why? Because so it can actually have different types of phases or what you say shapes, but in terms of structured mesh, so this is not acceptable. Even in unstructured mesh also you have some negative volumes, but it will take care of itself. But the basic criteria is, so you should give equal number of grid points. If you does not give equal number of grid points, it will internally generate the negative volumes, and therefore the mesh generation will not be possible actually. That is the main criteria. Okay, so similarly along y-axis also you can see, so let's say it is mapping here, let's say here we have, so this one, let's say it is mapping here, or let's say it is mapped here, so it will generate the negative volumes. So this is the main reason why we have to give equal number of grid points for the opposite phases or the boundaries in the domain. So opposite phases, so let's say we have this one, the opposite phase is boundary 3. So for boundary 4, the opposite phase is boundary 2. So therefore for opposite phases there should be equal number of grid points. That is the primary rule for generation of grid or mesh. And the other thing is, there is no need of giving same grid points along x direction and along y direction. So I'm talking about grid boundary points along x direction and boundary points along y direction. So the boundary points along y direction, so here in this figure 1, so basically I have taken it as 5 and 5. So there is no rule, or it's not mandatory that you have to take same 5 or same number of grid points along x boundary, along y boundary. Why? Because so whatever the values along x direction we have, so it will involve the flow parameters variation along x axis and y boundaries along y axis. So basically x and y axis they are actually mutually perpendicular and independent coordinates. Okay, they are not dependent coordinates, independent coordinates. So therefore you can vary independently, so along x axis, along y axis grid point. So what we need to capture along y axis, if it is, let's say you want to capture very thin layer, very thin layer thickness in the sense the distance along y axis, then you have to give more number of grid points along y axis. So it's not mandatory for us to see along x axis, so therefore we'll give less number of grid points. So it depends and it varies according to the situation. Now the second thing is, for generating mesh or grid points, it is not mandatory to have same number of grid points along x axis and along y axis, or let's say along the horizontal boundary or along the vertical boundary. But the first and foremost and important rule is, opposite faces or opposite boundaries should have same number of grid points. Okay, so now let's see basically an airfoil. So let me tell what's airfoil, then we will see how to generate a mesh for airfoil. Okay, so airfoil is basically, it's a 2D section of a wing. So if you take a wing, section of the aircraft, so let's say this is a wing section. So one side of wing or one part of wing. So this is called the root of wing, and this is called the tip of wing. Okay, so basically root is the section where it is attached to the fuselage. Fuselage is nothing but so where the passengers and the cargo, so everything is located actually. Okay, so if you take a section, so a cross section of the wing, so we get this airfoil actually, the 2D view. Basically wing is 3D, so airfoil is called 2D view. So in the airfoil also you have different types. So you have symmetrical airfoil and you have cambered airfoil. So symmetrical airfoil in the sense, so basically when we draw a line, let's say straight line, so on the upper surface and the bottom surface, so the distance, so here you can see. So if you take this let as a chord line, this horizontal line or the chord line is dividing this airfoil into two equal halves. Let's say this is half, this is half. These are equal actually. Okay, so then it is said to be a symmetrical airfoil. Now, what do you mean by cambered airfoil? So let's say we have this. So when I say cambered airfoil, so when you draw the straight line, so let's say it does not have the equal. So on the top it may be flat, on the bottom it might be curved. So when this chord line will not actually divide it into equal halves. Only the camber line. Okay, the camber line is nothing but the locus of the midway between the upper and lower surface. This is lower surface, this is upper surface. So this camber line will divide the airfoil into two equal halves actually. So this, if the camber line is above the chord line, this is called positive cambered airfoil. If the camber line is below the chord line, this is called negative cambered airfoil. Okay, so this is a small aspect or a small theory about airfoil. So now what we do, let us take any kind of airfoil. So how do we generate mesh for airfoil? We'll see. Okay, so how do we generate mesh for airfoil? We'll see. So now here you can see this face, the front face of the airfoil is kind of circular arc, or it's like a curved nature. So this is curved actually. Okay, so one most important thing while generating the mesh or drawing the domain is, so whatever the boundary of the geometry we have, so we have to adopt that actually. So what, so the domain is the area. So let's say this is the area I am drawing. So this is one thing. So this is kind of C. Okay, so now what, why I have drawn this actually? So we will see in detail, and then after we have the same this surface. Okay, so here if you see this diagram, so basically this is called airfoil, or you can say this as geometry in CFD or computational aerodynamics terminology. Okay, so this will act as wall. So this will act as a wall boundary, and so whatever the outer part, so we have drawn over the airfoil is called the domain. So here you can see this is called C type mesh. Okay, this is called a C type of mesh actually. So in the C type of mesh, so what do we have? So here this, whatever the circular arc we have in front of the airfoil, it has replicated here in the domain. Okay, so that's why we call it as a C type mesh or C type grid. Fine. So why we are adopted? Why? Because so whatever the curved nature we have on the airfoil, it should be same replicated to the domain. Why? Because whatever the number of grid points we give on the circular arc of this leading edge of the airfoil, same number of points will be here. Okay, so that is the main reason. So this is the overall domain. Now this domain can be divided into subdomains. Okay, why? Because the generation of mesh with this type of domain is also hectic actually. So what I will do is like I will divide this one into half. So here you can see this is subdomain 1, subdomain 2, subdomain 3. Okay, so subdomain 1, subdomain 2, subdomain 3. Now why I have created actually? So if I have not created this subdomain, so if I have not created this subdomain, so you can see that, so how many surfaces, there is nothing like closed envelope we have. So 1, 2, so 1, 2 and 3 and 4. So here when we generate overallly the mesh, so let's say I'm giving here 50 points only along this arc. So here also I should give 50. Why? Because this is the replica of this one. Next, so here this combination also should be with 50. Here also it should be combination with 50. So the thing is, so whatever the points we have here, 1, 2, 3, 4, 5, so on, let's say 50, it has come to 50. So it has to match along with this. Okay, so there is nothing like a closed boundary which has formed. So if you see this diagram clearly, now in order to set up a closed boundary, so we have actually drawn a line here. So with this, so how do I form a closed boundary? So let's take this as boundary 1, 2, this is 3 and this is 4. Okay, simple thing. So basically this is 1, 2, 3 and 4. So this is the one of easiest way to generate a mesh for the airfoil. So here what we have done, so we have taken initially airfoil over the airfoil. So if you want to generate mesh, so what we have taken a C type of mesh. So basically this is called C type grid or C type mesh. So next we will see what is O type of grid also. Okay, but here let's see what is C type of mesh. The C type of mesh, we have taken the leading edge of the airfoil, so which has the curved nature. So this thing we have replicated here over the domain. So that is what it is forming a C shape. So here you can see this is called the C shape. Fine. So with this, so what happened actually, so when I generated this, the grid points along this one and the airfoil should be same, but when it is same, the equal number of grid points also we have used, but it is not forming a closed setup or closed boundary. So that is the default. Okay, so if we want to have a closed setup or the closed boundary over this thing, so what we need to do is like we have divided into one subdomain. So initially we don't have this line. So when we have drawn this line, so it is divided the overall domain into two subdomains, subdomain 1 and 2. Now by creating the subdomains, what is the advantage we had? So we have created 4 walls or 4 surfaces or 4 boundaries. So this 1, 2, 3, 4. So these 4 boundaries or surfaces or the entities, so they form a closed setup. So this closed setup will actually generate a structured mesh. So by how? So it will generate lines like this, grid lines. So it will generate grid lines like this. Okay, so this is what we have. At a separate entity, it will generate grid lines like this. Okay, if we don't have closed setup, so the generation of mesh is complicated and it may form negative volumes. So that's why, so when we draw the overall domain, so we can divide the domain into subdomains, or let's say we can actually partition the domains by creating additional surfaces. So when we have drawn a line here, it has created additional surface and it has formed a closed setup. So this again you can see in the second domain. So an ease of mesh will be formed. Okay, so basically this setup is called the mesh. Okay, the mesh in front of the airfoil, so which is called leading edge. Now, so this C structure has obtained. So since the maximum thickness portion and the trailing edge portion, so they are very clear, straightforward. So here also you can draw a line, so that so from trailing edge to this point, so that it will form entity 1, 2, 3, 4. So basically the agenda here is to see so whether it is forming a closed entity with 4 surfaces or not. So that is the main thing that we are looking. So here, before, we don't have any line which is drawn from trailing edge of the airfoil uh, to the boundary. Okay, so when we have drawn, what happened, it has divided actually. So this will be the upper segment and this will be the lower segment of airfoil. So the upper segment of the airfoil, it has formed the structured mesh entity by forming the closed entity. So here on the bottom also we can do it. Now by creating these lines, so what we have done actually, so we'll see in summary. So again we'll see, this is the airfoil we have. So this is the C-type mesh we have. Sorry. So initially this is the mesh entity that we have. So now what happened actually? So we initially drawn a line like this. So already we have this line. We have this line. Okay. So initially when we don't have this, so what happened? So this is a complete C portion. So this is domain 1 and this is domain 2. So overall this is called the domain entity 1. But this domain entity is divided into 2 subdomains, 1 and 2. Now what was the difficult task that we had? So when we use grid points here, so what happened? So here this boundary and this boundary has to match with this. So the vertical thing has to match with this, but the horizontal things, so they may get the negative volumes. Okay, so that's why what we have done actually. So we have taken a line, so which will actually create this domain into 2 subdomains, which is 3 and which is 4. Okay, so when it has divided into 3 and 4, so what happened? So here we have formed a closed setup. Boundary 1, so BC1, so this is BC2 and this is BC3 and this is BC4. So with these 4 boundaries, so we have formed a closed setup by which we can generate a structured mesh. Okay, a regular structured mesh. Okay, so when we are drawn like this, so on the upper surface and on the bottom surface, in the leading edge of the airfoil, at the leading edge of the airfoil, so we are able to generate a C mesh. Okay, now here what happened actually? So here there is nothing, like we have the closed setup, so it's like open one. So here you can see it's empty, and whatever the grid points we have here, so here has to match this one, so this one has to match this one, but the somewhere here in this region it will form a negative volume. Why? Because there is no entity which is forming a closed setup. So that is the default which we have. So that's why at the trailing edge of the airfoil, so we have drawn an additional line. So when we draw this additional line, so this entity, okay, has formed a closed setup. So with this closed setup, we can draw a mesh which is on top surface. So let us take this as 5 and bottom as 6. So what happened here? This one. Okay, 6. So basically how many volumes we have? So first we have, this is the overall control volume 1. So this is control volume, we have divided into subdomain. Number 1, let's take this is 2, so 3, 4. So total we have 4 control volumes. Initially there were 2, the 2 again we have divided into 4. Why? Because we need to generate a mesh which is of structured and without negative volumes. Okay, so this is the story behind the generation of C mesh over airfoil. Okay, so it's not mandatory to use only a C type of mesh for the airfoil. Okay, so there is another mesh arrangement which is called O grid. Okay, so even for the O grid also, or O mesh, we can generate the grid points or grid setup over the airfoil. So let's see. So what is like O mesh? Now let us take the same airfoil again. Okay, so let us draw line here. Let us draw line here. So let us take this is arc. So let us take one more arc here. So this actually has simplified version of mesh which is called O mesh. Okay, so here this basically is nearly equivalent to O mesh. So where you can see that, so we have the O arrangement, the same trend will be followed. So here also you can again split into different domains to get into the structured way in the 4-4 manner or here. So anyway, but this is one sort of O mesh arrangement. Now if you see the previous one, so when we take this C mesh arrangement, or let's say if we take the O mesh arrangement, so whatever arrangement we make, the physics of the fluid should not change. Physics of the fluid in the sense, so whatever, let's say we have airfoil, so we are doing simulation for angle of attack, let's say at 5 degrees. Okay, so this domain should not affect the flow physics. So at 5 degrees of angle of attack, the airfoil will have a positive CL value. Okay, so let's say when we have used a one domain set of arrangement, so and if you get a negative CL at this positive angle of attack, so the meaning is that, so either you have used wrong boundary conditions or wrong mesh conditions or wrong set of domain setup. Okay, so whatever the arrangement you use, whether you use C arrangement, whether you use O arrangement, and the H arrangement, it is basically this one. So the same thing which we have, so the domain aspects. Okay, so here you might have some kind of thing. So this is adopted for the domain, boundary or the geometry, so which is in terms of the H conditions. Okay, so combination of CH is possible, and next O, HO and H also possible, but they are possible based on the geometries which are available for doing the simulation. So it's not like for all geometries you take a C mesh, or all geometries you take O mesh, all geometries you take CH mesh. It's not like that. So whatever the shape of the geometry we have, so here we have airfoil shape. So for airfoil shape, the O and the C were actually suited. That's why we have taken these kind of things. So if you have another kind of geometry, so which is suitable for this H and CH or HOH, any arrangement of mesh, that you can use. So this is called the different types of arrangement of mesh. Okay, so here you can see the boundaries, whatever it is available over this mesh or the domain. So 1, 2, 3, let's say we have 4 domains. So we say it as boundary 1, 2, 3. So let's say this is 1, boundary 1. Let's say BC1. This is BC2. This is called internal boundary, IC1. Let's say this is IC2. So when you are doing the simulation, so this will not come into picture, the internal boundaries. So basically they are joining two different domains. So this will not affect the simulation actually. Okay, so no need to worry about that. Since this is a wall, so this is boundary 3 and boundary 4. This is boundary, let's say 5. This boundary 6. So this all 6, whatever we have seen, 6 boundaries. So we have to give the boundary conditions for them. So BC1, BC2, BC4, BC3, BC5 and BC6. So we have to clearly mention what are those boundaries actually. Okay. So before generating mesh, so we will draw the geometry and generate the domain. When you generate the domain, so when we assign the grid points and when we generate mesh, then immediately you have to identify the boundaries. What are the internal boundaries? What are the external boundaries? So external boundaries are responsible to have the flow input and flow output. Okay, so input flow, you have output flow. Okay, so therefore we actually have to give proper set of boundary conditions to see that the flow physics is properly verified and validated. Then only we can do the actual set of problems. Okay, so this is the main criteria of need of generation of mesh. Okay, and different arrangement of grid points. So we will see in detail. So basically what is the conditions imposed on the mesh, what type of boundary conditions, and then after what is initial conditions and boundary conditions, types of boundary conditions, types of initial conditions, and can the boundaries move or remain stationary. So these things we will see in detail in the next module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.